Hello students, welcome back. In the previous class we discussed real numbers. In real numbers we discussed about Euclid's division lemma, and you all remember that Euclid's division lemma states that given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r is always less than b but greater than or equal to 0. And we also have done some questions, some applications of Euclid's division lemma in real life situations. So today we will go ahead with the next theorem, that is fundamental theorem of arithmetic. What does the theorem state? According to fundamental theorem of arithmetic, every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Let us see it in detail. Fundamental theorem of arithmetic says that every composite number. Now, what is a composite number? All of you know what is a composite number? A composite number is that which can be as the product of its prime factors other than the number itself and 1. So every composite number can be expressed as the product of prime numbers, and the most important part is this prime factorization is unique, and the order of the factorization doesn't have anything to do here, because whatever the way you write down, the product will be always the number, the composite number. So we can prove it by taking some examples. Let's take an example, 468. This 468 can be factorized in different ways. Let us at least see finding the prime factorization of 468 in two different ways. (468) can be divided by 2, all of you know, and you will get 234. Now 234 can be again divided by 2, you will get 117. Now 117 we can divide by 3 because 1 plus 1 2, 2 plus 7 is 9. So once you divide it by 9, you will get 39. Now 39 again can be divided by 3, you will get 13. So what can you conclude? 468 can be divided by 2, again 2, 3, 3, 13 and 1. So 468 is equal to 2 into 2 into 3 into 3 into 13. 2 into 2 into 3 into 3 into 13. That is 2 square into 3 square into 13. So this is the first way of prime factorizing. Now let us see the second way. Before that, let's write it down. 468 is equal to 2 square into 3 square into 13. Now let's go for the prime factorization of 468 in a different way. Instead of beginning division by 2, let's divide it by 13. So we will get 36. Now if you divide 36 again, you can divide it by 2 also, you can divide it by 3 also. So let's divide it by 3. So you are getting 12. Again divided by 3, you will get 4. Divided by 2, you will get 2. And again divided by 2, you are getting 1. So 468 is equal to 13 multiplied by 3 multiplied by 3 multiplied by 2 multiplied by 2, or 13 multiplied by 3 square into 2 square. Now let us see. We have prime factorized 468 in two different ways. The first one is this one, and the second one is 13 into 3 square into 2 square. Now what can you observe here? 2 square is here, 2 square is here, 3 square is here, 3 square is here, 13 is here, 13 is here. So their order is different. So 468 can be represented by the product of these prime numbers only, but order is different. So you don't have to worry about the order, but it is sure that with these prime numbers, if you multiply, you will get only 468. That is why it is written that it is unique. This composite number can be made as a product of only these prime numbers. It cannot have any other prime factor other than this one. So this prime factorization is unique. So now we understand what fundamental theorem states. Now let's take some more examples. Now let's take small numbers. 72, if you divide 72 by 2, you will get 36. Divided by 2 again, you will get 18. Divide by 2, you will get 9. Divide by 3, you will get 3. So 72 is 2 cube into 3 square. Similarly, 4 is equal to 2 square. 1771, if you divide by 7, you will get 253. By 11, you will get 23. So 1771 is 7 into 11 into 23. Again, let's take a third number, 1050. If you divide it by 2, 525. Divided by 3, 175. Divided by 5, 35. Divided by 5, 7. So now see these numbers. 4 is 2 square. 72 is 2 cube into 3 square. 1771 is 7 into 11 into 23. 1050 is 2 into 3 into 5 square into 7. Now you can see that the 4 cannot be represented by any product of other prime numbers. It means that 4 is only 2 square. You cannot have any other prime numbers in 4. Similarly, 72 cannot have any other prime numbers other than 2 and 3, and 2 appears 3 times and 3 twice. Similarly, 1771 can have only prime numbers 7, 11 and 23. 1050 can have only prime numbers 2, 3, 5 square and 7. So this is why the fundamental theorem of arithmetic states that the prime factorization of every composite number is unique. Now let's go for the applications. Let's take a case. Let's look at this question. Consider the numbers 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. Now, you need to say that whether it is 4 to the power 1, 4 square, 4 cube, 4 to the power 4 or 4 to the power 100 or 4 to the power 1000 or any power of 4 where n is a natural number will end with the digit 0. That is the question. Now, how to know that? It's very simple. What we need to do is that look at the base of the number, that is 4. The 4 can be prime factorized, that is 4 is equal to 2 into 2. Now, what are the prime factors of 4? Only 2 and 2. So, according to fundamental theorem of arithmetic, a composite number can be expressed as the product of primes, but the prime factorization is unique. Therefore, 4 cannot have any other prime factors. So, let's see how we will start with. Now, if you want to have a number ending with the digit 0, means that is a multiple of 10. So the number must have prime factors 2 and 5. Now, what are the prime factors of 4? The prime factors of 4 are 2 and 2. It does not have prime factor 5. So 4 to the power n cannot end with the digit 0 because it does not have 5 as a prime factor. And now you will think that it is raised to power of something, then it can be, but it will not be. Why? Because fundamental theorem of arithmetic states that the prime factorization of a number is unique. It means that 4 cannot have any prime factor other than 2. It cannot have a prime factor 5, so the number will not end with the digit 0. So we can write like this. The prime factorization of 4 are 2 and 2. Therefore, 4 to the power n can be written as 2 to the power 2n. It does not have a prime factor 5. Therefore, 4 to the power n will not end with the digit 0. Let's take another example. Find the LCM and HCF of 6 and 20 by prime factorization method, which you have already learned in smaller classes. So I don't think that you need further explanation on it. Still, let's just see. You need to find the prime LCM of 6 and 20. So 6 is equal to 2 into 3. 20 is equal to 2 into 2 into 5. So it can be written as 2 to the power into 3 to the power 1 as 6, and 20 can be written as 2 square into 5 to the power 1. Now comparing these two, 2 to the power 1 is here, 2 square is there, higher power is 2. And again 3, only one 3 is there and only one 5 is there. So while finding the LCM, what we do? We take the higher powers of the number. 2 square, 3 to the power 1, 5 to the power 1. So you multiply it, you will get LCM as 60. And HCF is simple one, the common factor, highest common factor. Both of them have only one common factor, that is 2. So HCF is 2. So these types of questions you can expect for 1 mark, finding the LCM and HCF. Now let's go for another question. That is, find the HCF of 96 and 404 by prime factorization method, and hence find their LCM. Now this is a keyword, hence find their LCM. It means that first you need to find the HCF, then using the HCF you have to find the LCM. So for that you need to know this property. The property is that LCM and HCF of two numbers is the product of the two numbers. This property you studied in the smaller classes. What is that? HCF into LCM is the product of the two numbers. HCF into LCM of two numbers is product of the two numbers. You multiply the two numbers, that will be equal to LCM and HCF of the two numbers. So let's come back. First you use the prime factorization method. 96 can be prime factorized as 2 to the power 5 into 3, all of you know. Again you can prime factorize 404 as 2 square into 10. You do the prime factorization, then you will find that HCF of them, that is the highest common factor. 2 to the power 5 and 2 square is 2 square is common and there is nothing else common, so HCF is 4. Now you use that property, don't directly find LCM because here it is given hence find their LCM. So to find hence find their LCM means you use the property HCF into LCM equal to product of the numbers. 4 into LCM is equal to product of the numbers. So product of the numbers divided by 4. 96 into 404 by 4 equal to 9696. Understand the property? LCM into HCF equal to product of the two numbers. So what have we done? LCM we know, we don't know. HCF we know 4. 4 into LCM is equal to 96 into 404. Therefore LCM is 96 into 404 by 4, you will get 9696. So thank you students. Now we will give you some assignments on the basis of this. You go and solve it and ask us doubts during your interactive time. Thank you.